So welcome to the lecture Introduction to Cryptography, and welcome. And today we finish the chapter of digital signatures, which is an important tool for cryptography and also used in practice. However, maybe not the most exciting thing, since we get into cryptographic protocols later on, where we have the most mind-bending protocols. Okay, so just repeat, what is the digital signature? So we have in key okay, I have to. Hardware attack. So we have key generation, where we produce a public-private key. So digital signature was an outcome from the invention of asymmetric cryptography, since we always need the public-private key pairs, and suddenly it was possible to do something like that. It was not, could not imagine that this was possible before, and it also gave way for more complex things that people couldn't imagine. So we have key generation, we have a signing algorithm, and we have verification. This is very frustrating. So my bachelor thesis was about programming a digital signature scheme. And so I wrote a lot of code. And then what happened is that the code was computing, was very slow computer. And then finally the answer was yes or no. It's just, it's not like you code something, you get something complicated, and when you decrypt it, you just get something which is obviously constructed by some other code that you have written, and then you put it in your algorithm, and the answer is yes or no. So, which is, you cannot really show off with digital signatures. So, and if you produce something wrong into it, then its answer should be no. If you put something right in, then it's yes. But you cannot be sure that somebody can really find some mistakes in this. But nowadays we know that we can make additional signatures, which is from the 90s, the result, as secure as the underlying assumption that we have. So, which is the security. So we can withstand the most harsh attack, which is an adaptive chosen message attack, and you cannot even falsify a single message. But we don't go into the thing that I programmed 100 years ago. So we will look at what's the current state, and the current state is always the same. So we have a public key crypto system. We have some key generation, and we just use the decipher algorithm in order to sign the algorithm, and then we send the message and the signature. So this is also different from the encryption, is that we send the message. It's not a secret. And then there's some way to check it. Okay, so we already start some discussion, and we continue with the basic scheme based on RSA, which is how we teach it in the first semester of if you study computer science. That we look at RSA, because RSA is a very nice scheme where you have the public key, which is a multiplication of two prime numbers. Then you have these two pairs which multiply together to 1, modulo the Euler phi function. And for signing, what we do is we use one of the key pairs, which is usually used for decryption, and then we have to check with encryption whether this is really the same thing. Now, in RSA, everything is symmetric. So you can, D and A doesn't have a particular meaning. So it's not quite clear why we change, where you change for encryption and decryption. This becomes clearer if you look at a variant where we have, for example, El-Jamal. However, RSA is very interesting to study, especially since there are lots of attacks on RSA. And lots of mistakes you can do. So you can talk a lot about what can be wrong, and we can learn how you can actually improve on that and what you have to be careful about. And the first thing that is obvious is since we have this encryption key publicly available, you can start with a signature here, sigma prime, and compute sigma e prime, and just send this as a message. And so you have a message and a valid signature, and you hope that taking some number to some power doesn't produce anything useful. So you basically have a signature of garbage. That's what you get out of this. But it is an attack, and it says that you can produce signatures, which might have some value, because you could say, oh, this is a message in Finnish. Nobody can read it except the Finnish people, but I can prove that I can sign things like that. Okay, so that's something we had. Now we can also use the semi-homomorphism of RSA. So assume that we have two messages and they are signed. And okay, semi-homomorphism means that if you multiply the messages, then the encrypted code is the multiplication of encrypted code of each message, which at this moment is not used in a useful way, it's just for attacks. But later on, we will really look into that and try to use it in order to make new protocols. So that means if you have two messages, then the multiplication of the two messages can be signed. So just imagine that the message has 100 euro and the other message has 10 euro just as a digit. So then you have a signed message of 1000, which you just put into maybe a message stream and say, pay Bob 100 euro, and 100 is one message. And another one you get from Bob 10 euro, and then you combine it, and then you pay Bob 1000 euro. That's a very stupid way of attacking, but we see that we have to do something with a message before we just use it before. What we also can do is a chosen message attack. A chosen message attack is you want to forge a signature, but you are allowed to ask for one signature. So like that Alice grants you, okay, I have this new system and I want to show that it works. Give me any document, I sign it for you. But only one. Yeah. And so what Eve, the attacker, does is ask Alice for a signature of this message, which sounds completely harmless in the sense that it takes the original message where Eve wants to have a signature and multiplies with a random number to some power. Now, the interesting thing is, which will be used later on very, very often, is that if you take a random number and take a power of it, then you don't have any structure. It completely looks like a random number. And the same number happens with the same probability. And if you multiply with a message, and unless it's zero message, which is also a bad idea, you get a product which is again uniformly distributed in Z star n. So every message has the same. So you cannot see from this message that there's something hidden in it. It's just that we know it, and we use the knowledge that, and Eve uses the knowledge that she has some basic hidden idea what is inside it. But this is really not there. It's just that Eve has this knowledge. Now Alice sends the signature, and by this very nice operation, what happens is that as a result, I can, you can see R to the E, so we can say this is the same as R to the E times D times M to the D, and so this will be R. So what we have is we just have to divide this by R and we get the signature, which comes from homomorphism, of course. So that's an attack which is possible. Which, yeah, so we want to have, again, so let's look back. So we want to have a signature which is secure against the strongest attack. And what we also want to have is we want to have a high security of a forgery. So we don't want even have the simplest one. And what we have now is that we have selective forgery for Joe's message attack. So it's not so good. So we have to repair this somehow. Okay, now things can be even worse. And if you are using an RSA key for encryption and digital signature, then this is a really bad idea to do so. Because you can have a new form of attack. So it also means that and just remember that creating new RSA keys is, well, it's complicated if you choose a new N, because you have to find new prime numbers, and this takes some time, not too much, but it takes some time, as we have seen. But E is very cheap, so you can actually have a new E, because the only thing that you have to do is the extended Euclidean algorithm to compute the fitting D. Okay, so but if you want to save this, say I will use the same key for encryption and digital signature, so there's the following attack. So the attacker Eve has received an encrypted message, which is this thing. So this is the encryption from RSA. And now what he does is, this is R. Sorry, this is a typo. Eve sets a random number. Usually random numbers are called R, not E. Selects a random number and computes this. So it takes a random number to the power of E and multiplies with C. Okay. What is C? I think that should be C here. I think we have some typos here. So this is because it's usually with cipher. Okay, so we have this is the cipher, C is the cipher, R is a random number, and we compute X. Now this is the X, not this one, and we send it to Bob. Okay, now Bob signs this. So we have an attack where we are allowed to ask for a signature, which should be harmless because you get a document and say, okay, this document looks fine to me. I sign it, that I have seen it, that's my document, I've received it. And so you sign the document, you get X to the D. Okay, now let's see whether I corrected the slide correctly. So what we have is, we have X to the D, which is equivalent to R to the E times C to the power of D, which is equivalent to R to the E times D, and C is M to the E times D, and this is all modulo N. So this is equivalent to R times M modulo N. And we know, and Eve knows R. Eve knows R. Knows R. So with this signature, Bob sends basically the encryption of a message. Does Bob know that it's doing it? Well, let's see. Again, let's look at this X. So the X is constructed by multiplying by a random number to the power of E, which is a random number from Z star N, again. And C is fixed and was sent by Bob, but Bob has no way to know that this is somehow connected to its original code. There's no way to find it out because every possibility has the same probability. So basically it's already too late. Now, Eve can compute the original message by taking the inverse of R and multiplying it with x to the d modulo n. And then Eve can say, here, sign this, sign that. And for each signature, Eve gets a decrypted message. It's very nice. And actually totally destroys the RSA. So, okay, so don't do that. That comes from the fact that we actually change the roles. So what we do is we somehow use our private key here in order to do the signing. So we are giving away something in a way which we don't know what happens. So can we repair this by replacing the role? Hell no, because if you give the decryption key to the verifier, you can do this all himself. So he has everything. Okay. So how do you solve it? So you can solve it by, well, don't sign anything. Don't sign everything. So you have to be restrictive when signing random documents, because there could be some structure in the one-way function, and there must be some structure in one-way function because it's an asymmetric cipher. You have some trapdoor information which helps you to decipher it, which the other one cannot use. So there's always some kind of structure in this public key, in this asymmetric cryptography scheme. So the easiest way is don't sign M, sign MM. Yeah, so this is a good idea, since if you take a random number and you can check, so let's say how large is, let's say we think of 1000 bits. Yeah? And we have 1000 bits just to have a number. And let's say, and you say that F is from 1 to 500. And what is the chance to get WW? What is the probability that R is a random number, which is WW, under the assumption that R is chosen randomly from this set? What is the probability? So what is the probability that you get basically a copy? And not all of you. So probably that you get a certain bit is 1/2. Randomly, if I get 2 bits, it's 1/2 to the 2. Square of which probability? 500. So you say 500, 1/500 square. Is that your answer? So it must be something like that. So we just have to argue what's in the denominator. So we fix the first one when the second one is determined, yeah? Yeah, it's 1/2 to 500. Because you have 500 bits, which is very low. It's very low. You can say that 2 to the 10 is 1000, so it is basically 10 to the minus 150, which is a very small probability. So you shouldn't play this lottery, because it's much more likely that you will be struck by lightning and a meteorite at the same time. So no, actually, just I mean that if there exists one W in this form, that's what I mean. So that it has this form, because the first 500 bits can be anything, but the next 500 bit must be certain structure. So that's the first one are somehow you make with random experiments. You have the first 500 bits, so it's somehow fixed now. So this happens with probability 1, the first 500 bits, because everything is allowed, but the next 500 bits must be in this form. And so you're stuck with 500 bits which have to fall in this way. Yeah, and usually humans are very bad in calculating likeliness. Yeah, especially when it comes to, micromods, micromods. Yeah, I told you maybe micromods, that is one micromode is 1/millionth the possibility that you die today. That's a micromode. And you have approximately, depending on your age, you have 10 to 20 micromods every day. And if you smoke, you get some more. If you go by bike, you get even more. Or if you have some other hobbies which might be dangerous, you get even more. And we are really bad in actually calculating these kind of problems. Although most of us are very interested to survive this day somehow. Which, if you look at people, what they do, says that maybe everybody is really bad in probability theory. So it must be really worth to, of course you can stay at home and lock your door, but then you get some additional micromods because you don't exercise and you don't have sun. That's, yeah. But maybe survival is not the only goal in your life. I don't know. This is, yeah. I'm interested in these kind of things. When it comes to certain dangers, that you have to take risks at some point, but if you want to take risks, you have to know what to do, and that's a risk I would be taking, because that's if somebody makes a process and this happens with this probability, I can safely swallow that pill. That doesn't actually affect me at all. Okay, just look up how many people are struck by lightnings and how many people die from meteorites, and multiply it, and then you get probably which is way higher than this one, if it's the thing. So, yeah, I looked it up. Okay, so this is a secure method which works, but in practice, other methods are used. First of all, it's overkill from a security point of view, because it's more likely that somebody just has the key. And the other thing is we're wasting 50% of the bits. So what you do is you do a signature with a hash function. So we have a cryptographic hash function. First, we apply the hash function and sign it, and we send this. And then we check we have to check two things. So first of all, we calculate the message with a hash function, and then we check whether the signature has this format. So now we have the idea, so that these are all messages, and these are the domain of a hash function. So this is let's say 0 to 1 to 1000 bits. And then you map to this domain to the hash functions. And hash functions, I think the whole idea of hash function is that you don't take a large domain. So that you have 256 bytes or 512 bytes or something like that. So in the best case, so let's assume that you're mapping this to 122 to 128. So there's a good chance that you don't hit it. But still, this is too restricted, in the sense that you are not taking all the possibilities. However, the idea that you should never sign an original message is the hash then decrypt paradigm, because most of the attacks were basically built on the idea that you sign some garbage which has some kind of internal structure. Okay. However, a message with the same hash value have the same signature. That means that if you lose the security, if a hash function is broken, then even if you are very good with your signature scheme, then this is broken too. So you're actually becoming dependent on the security of a hash function, which hash functions will all be breaking over time. Will be all broken over time, because they don't work in principle, because you map infinitely large message space into something which is finite. Okay, so the idea is now to use full domain hash functions, which maps to the full Z star n, and this is not the case if you use the common hash function which are around. because RSA is actually using something bigger. Okay, so what we do is we use probabilistic signature schemes, which are described on the left side. I took the liberty and made a diagram in order to find out what it's doing, because actually I'm as lost as you reading the code. Okay, so, but maybe it's not the planar depiction, but it's also because of the parameters going into it. Okay, let's go through that. So first of all, this probability signature scheme is something you can do with a lot of asymmetric cryptographic systems. So basically, we start with a chapter function, which could be RSA, but not necessarily have to be. So you have an encryption function, which is public available, and you have a decryption function, which is, next typo, which should be, I don't know why I make typos. It's just that I keep myself entertained through the lecture. Probably C to the D. Okay. Now, this is C to the D. Okay. We know how it works. Okay, so later on, actually after each lecture, I go into the slides and look into what I have annotated here and try to correct the mistakes that have been on the slides. But sometimes something slips through, and if you see something, you can put it in the forum or send me an email when I will repair it, so that in the end, if you prepare your one sheet of paper, you copy from slides which are correct. So, and also that means please check the date on the first slide. I update always the date when I change the slide, so that you have the most current one and not some kind of old ones, because I keep on working on that in case I find some mistakes. Okay, so now what we do is we have another thing, which is a pseudo-random bit generator, which takes a small input and produces a large output. Pseudo-random bit generators are, they are actually a topic on its own. So they are also cryptographic. Pseudo-random bit generators, you shouldn't use the simple modulo things that you know maybe from hash function and data structures. Okay, assume that we have that. So we take a small W and produce a larger output, which consists of two parts. One has size k, the other one has the rest of it, n minus L plus k, which just fits that we can fill up the decrypt function. And we have the hash function. Okay, so that's everything. So we need a bit generator, the hash function, and the chapter function, and so what you do. Okay, first of all, we randomize. So we use a random seed, a nonce, a random number which we use only once. The best way to make sure that we only use it once is just to take it randomly, because the probability of taking a random choice twice is very low. In this context, how do you get random numbers? Yeah, I see there's a problem. Some of you believe that this universe is deterministic, and there is no randomness at all. So it's like a contradiction itself. Some of you who believes that this universe has some random numbers for you left over. Oh, all deterministic. I knew that this was happening. So if you have heard some quantum theory lecture, then you believe in randomness. However, so how do you get randomness? That's a hard thing. So somehow, because on the processor, it's not easy to get them. Now we have randomness a lot. So one way is to take a radioactive decay and just watch when the next click is coming, and if it's coming in odd or even time, you can use that. Or which you probably don't have in your microprocessor. Usually, if your microprocessor is suffering from radioactive decay, you're probably too close to a nuclear power plant or some explosion. The next easier thing is to listen to noise. So if you are lucky enough living next to a highway, you just take a microphone and you get lots of noise from a highway. Yeah, that's the power of noise. Or you just take electromagnetic waves. That's one way. How do you get access on your microprocessor to these kind of inputs? Well, the answer is short, you don't. So all these guys, Beere and his fellow comrades, they have every day we're working against randomness produced on a microprocessor, but they just erased everything. So that we have no input to get random numbers, which we need all the time in cryptography. So we need randomness, which they could provide to us, and they don't give it to us. And I keep telling this for decades. Nobody's doing something. So if you go into microprocessor design, please give us some random bits. Yes, you can buy random bit generator chips, and put it into your hardware design. But I have not seen it yet. If you know something, please let me know. We have neural chips and all this other crap. So, but random numbers, very old thing. Okay, so we already managed one line of me telling you how bad it is to. So what you do is you take some random Cs, people putting keystrokes, other process running a computer, putting it to pseudo-random generators, and then outputting it somehow. There's a whole theory about how to get randomness. Now the next thing is, so we have a random input. We use this with a hash function and produce this W. So we combine this to the input, and then we have a message M with W, which is now the randomized hashed code. And this is already one input that we use. So we get W here in the decipher and decrypt operation. Then we take the same number here, which has some randomness, put it into the pseudo-random bit generator, where the later half is used here as the input, G2 of W, and the first half is XORed with a random bit as well, G1 of W, XOR. So this is the thing that goes in, and then you decipher it, and then you get the signature here. And then we send it. Okay. How can we verify that this is a valid signature? Yeah, we have to do this somehow backwards. Yeah. So what do we have at the receiving end? At the receiving end, we have a message, and we have a signature, and we have a cipher operation. So basically, we can start here and go upwards from here. Okay. And if we can go upwards from here, what we see is that we are missing random bits somehow. So we have to get the random bits somehow. Let's see how do we get it. So, but we can produce the random bits, and that's why we have this XOR, because we have W, we can go into this function, and then you can produce the random bits here and go upwards, and then we have everything to check the hash function. Okay, so I made this picture. Verification. So this was the signing. So we start with the signature and encrypt it with a public key. So we get 3 components. The crucial one is this W. The W is the hash function with the random bits, which we don't have so far. But we can create it by taking the pseudo-random bit generator, take the first half, and use XOR as the inverse of the XOR function, and combine it with the second part T, which is coming out of the encryption. And then we get R, and with R we can check whether this is the correct output. So this should say yes here. So we can now produce the hash function with original H with this randomized bit, which we don't send. So we can check it. So on the other side, we can check whether we have used the pseudo-random generator in the correct way by comparing it to the output here. Okay, so that is the whole function. I hope I have put it here correctly here. W, yeah, this looks good. Okay. So now we have to check two things. So we check whether the pseudo-random bit generator is fed with the correct W, and whether that this W is really using the correct Rs. And you can, well, it's possible to prove under certain assumptions about the pseudo-random bit generator and the hash function that this probabilistic signature scheme is secure if RSA is secure. So you can prove that if you have the three components are secure, then this is also working and you cannot be falsified. And we also get rid of a lot of problems. So basically an adaptive chosen message attack doesn't work, and many other attacks doesn't work because the signature is using some random numbers and you cannot use all of them. There's a connection between the random seed and the output, and the random seed itself is also connected to the signature. So that's why on an intuitive level this is working. Okay. Now we have done signature schemes for RSA. So we can also do this for El-Jamal. But I think it makes sense to make the break here because we are also using the elliptic curves, which is very close to El-Jamal, so we should have them together in one block.